Are you familiar with engine management in petrol and diesel engines? Even if you are, before you start this CBT program on emission control, it's worth having a brief look at the contents of these other CBT programs, which will be useful when working through this program. Move the mouse over the titles of the individual CBT programs. Chapter 1 of this CBT program describes the reasons for and the goals of emission control. Firstly, the continued growth in individual transportation and the environmental consequences of this are dealt with. Then various national regulations and engine-related measures for limiting exhaust emissions are presented. Finally, the prerequisites for emission control are explained. The unrestricted mobility that individual transportation has given us is now part of everyday modern life. Likewise, the supply of food and consumer goods of all kinds to all areas by long-distance haulage is taken for granted. The downside to this improvement in our quality of life, however, is that the air and the environment are being increasingly polluted by harmful emissions from vehicles. Let's take Germany, for example. How much of the total volume of pollutant emissions comes from road traffic, do you think? Select a figure from the pie chart. As you can see, road traffic is responsible for around 20% of all emissions in Germany. The combustion of the air-fuel mixture in both petrol and diesel engines produces not just carbon dioxide and water vapour, but pollutants as well. These are carbon monoxide, nitrogen oxides, sulfur dioxide, and hydrocarbon residues. Combustion of diesel fuel also produces soot particulates. An additional consequence of road traffic is the formation of fine dust. Fine dust is created not just from diesel soot particulates, but also from the abrasion of tyres, brake linings and pads, clutch linings, and road surfaces. Click on the names of the pollutants to learn more about the effects they have. The chemical symbol for carbon monoxide is CO. Carbon monoxide is poisonous because it reduces the ability of the blood to absorb oxygen. Nitrogen oxides, NO and NO2, are usually referred to as NOx. They irritate the mucous membranes, affecting breathing in particular. Sulfur dioxide has the chemical symbol SO2 and is a colourless, poisonous, pungent-smelling gas. In high concentrations, sulfur dioxide burns the mucous membranes. Hydrocarbon residues are usually abbreviated to HC. In persistently high doses, unburned hydrocarbons are carcinogenic. Diesel soot consists of ash and unburned hydrocarbons. Emissions of soot are measured in grams per kilometre and are referred to as the particulate mass, or PM for short. Soot particulates are thought to be carcinogenic. Like diesel soot, fine dust is measured as a particulate mass, but in smaller units of micrograms per cubic metre. Fine dust has been categorized by the WHO, the World Health Organization, as harmful to health. All the pollutants listed here are not just harmful in the short term, they have long-term effects as well. The short-term consequences of the increased pollution of the air we breathe and the atmosphere are smog and fine dust. The long-term consequences are acid rain and the greenhouse effect. Many countries in the world, for example the USA, Japan and the European Union, have set limits for the levels of pollutants in the exhaust gases of vehicles. Most of the world's emissions regulations have been drafted by the US CARB, the US EPA, the EU and Japan. You can learn more about the exhaust gas legislation drafted by these legislative bodies and the areas covered by clicking on their names. The abbreviation CARB stands for California Air Resources Board. Though the emissions regulations for the maintenance of air quality that are produced by this authority are only applicable in California, they serve as a guideline for emissions legislation in other U.S. states. The American Environmental Protection Agency, EPA for short, stipulates emissions standards for all U.S. states except California. Many other countries, for example Canada, Australia and Brazil, use EPA legislation as a basis for their own. EU emissions legislation applies to the countries of the European Union. The emissions regulations of many other nations, for example India and China, are based on the European standards. Unlike other countries of the Far East and Australia, Japan has its own independent legislation. All the legislation named encompasses separate emission standards for passenger cars and trucks. Further information on this topic can be found in the glossary of technical terms. Emissions legislation makes a distinction between vehicles with petrol engines and vehicles with diesel engines. In addition, vehicles are divided into the following classes: passenger cars, light commercial vehicles, heavy commercial vehicles, and heavy construction, forestry and agricultural vehicles. Vehicles are classified by a reference mass, that is, by vehicle weight. The emissions standards and limits applying to passenger cars and light commercial vehicles are different from those for heavy commercial vehicles. Type approval tests check that the emissions standards are being adhered to. Here, new vehicle models have to complete special test cycles under very specific load conditions. Where passenger cars and light commercial vehicles are concerned, the complete vehicle is tested on a roller dynamometer. In the case of heavy commercial vehicles, only the engine undergoes the test cycle on an engine test rig. Click on the diagrams to learn more about the corresponding emissions tests. Depending on vehicle class and whether the vehicle has a diesel or petrol engine, the European emissions standards impose limits on the emission of the following pollutants: carbon monoxide, hydrocarbon residues, nitrogen oxides and, in the case of vehicles with diesel engines, soot particulates. History shows that the limits for these pollutants have been lowered with each new emissions standard, and pollutant limits will continue to be cut in the future too. Reducing the average fuel consumption is the most obvious way of reducing emissions from vehicles. Why is that so? When combustion occurs in the engine, carbon, the main component of fuel, combines with the oxygen contained in the intake air to form carbon dioxide and carbon monoxide. Partially burned fuel components produce the harmful hydrocarbon residues. The more fuel is used, the more carbon monoxide, carbon dioxide, and hydrocarbon residues are released as a result. It can be said, therefore, that if fuel consumption is reduced, hydrocarbon emissions will be reduced in the same proportions. This applies to both petrol and diesel fuels. Design and operation measures to minimize the formation of pollutants, particularly in the engine warm-up phase, include an improved pre-glow system for passenger car diesel engines, secondary air injection for petrol engines, exhaust gas recirculation for passenger car diesel engines and some petrol engines, and for both engine types, adaptation of the shift behavior of the automatic transmission, and suppression of electricity generation in the alternator after a cold start. Now compare the untreated exhaust gases from a petrol engine operated at a lambda value of 1 with those of a diesel engine operated in partial load mode. To do this, click on the two columns. Here you see in both cases that the proportion of pollutants is, on the whole, small. However, it's impossible to prevent their formation completely, even if more engine-related measures were to be introduced. Therefore, the exhaust gases must be purified. The technique chosen in each case depends on the type of engine and on the fuel used, because the latter also determines the composition of the pollutants. Click on the proportions of pollutants to learn about their composition. Diesel engines operate with an excess of air. Therefore, they create relatively large amounts of nitrogen oxides, NOx, during combustion. As diesel fuel is in the form of a mist when burned, soot particulates also form. The petrol engine produces fewer nitrogen oxides than the diesel engine. In the petrol engine, nitrogen oxides and residual hydrocarbons are present in a relatively equal ratio, and can therefore be neutralized more easily along with the carbon monoxide. Petrol is in a gaseous state when burned. As a result, petrol engines do not produce any measurable amounts of soot particulates. What effect does the air-fuel mixture ratio have on combustion temperature and the formation of pollutants? As you already know, diesel engines are normally operated with an excess of air. The combustion temperature and the proportion of nitrogen oxides in the exhaust gas are therefore relatively high. The amounts of soot particulates and hydrocarbon residues produced are relatively low. Can you think what would happen if the proportion of oxygen in the air-fuel mixture is reduced by using exhaust gas recirculation? Drag the answer options into the corresponding columns in the table, then confirm by clicking on OK. What effect does mixture formation have on the combustion temperature and formation of pollutants in the petrol engine? At full load, petrol engines are operated with a rich mixture, that is, with relatively more fuel, in order to protect the engine and the exhaust system from excessively high thermal loads. Consequently, fewer nitrogen oxides, but more carbon monoxide and hydrocarbon residues are produced. Have a think about what effects operation with a leaner mixture, that is, with a higher proportion of fresh air, would have in comparison to this. Drag the answer options to the corresponding columns in the table and confirm by clicking on OK. You have learned that different concentrations of pollutants can arise in the exhaust gas depending on the type of engine and how it is operated. The three-way catalytic converter has become the tried and tested method of exhaust gas after treatment in the petrol engine, because in it, nitrogen oxides, carbon monoxide, and hydrocarbon residues all neutralize each other. Petrol engines with direct injection, which can also be operated with a lean mixture, require an additional NOx storage catalytic converter. Vehicles with diesel engines are fitted with an oxidation catalytic converter to reduce the amount of carbon monoxide and hydrocarbons in the exhaust gas. The formation of nitrogen oxides is already reduced by the use of exhaust gas recirculation. Soot particulates, which are present in greater amounts as a result, must be after-treated by means of a diesel particulate filter. Heavy commercial vehicles without exhaust gas recirculation can be fitted with a selective catalytic reduction system, SCR, for the after-treatment of nitrogen oxides. In the European Community, which exhaust gas components are limited by emissions regulations? Select these components, then confirm by clicking on OK. Exhaust gas purification is required if the legal limits for pollutants cannot be met through engine regulation alone. This applies equally to passenger cars, vans and trucks. The exhaust gas composition of vehicles with petrol engines is different from that of vehicles with diesel engines. In each case, the exhaust gas composition can be varied to a certain extent by engine regulation. Exhaust gas after treatment in petrol engines is achieved by means of a three-way catalytic converter, and in the case of petrol direct injection engines, with an additional NOx storage catalytic converter as well. The three-way catalytic converter is monitored by the oxygen sensors. the NOx storage catalytic converter by corresponding additional sensors. The term catalysis refers to the change in speed of a chemical reaction as a result of the presence of a special substance, the catalyst. The catalyst itself is not consumed in the process. Drag the catalyst to the container containing nitrogen monoxide and carbon monoxide and observe the reaction. You can see how the nitrogen atoms N give up their oxygen atoms O to the carbon atoms C. This reaction would also take place if a catalyst were not present, but would take much longer. In vehicles, the term catalyst is used not just for the material, but also for the entire component, the catalytic converter. It forms part of the exhaust system and is used to after-treat the pollutants in the exhaust gas. The catalytic converter is installed as close to the engine as possible, downstream of the exhaust manifold, so that the exhaust gases flowing through it can quickly bring it up to operating temperature. The catalytic converter consists of a ceramic monolith with a honeycomb structure. The surface of the monolith has an extremely rough structure. This increases the contact area. The surface of the ceramic monolith is coated with platinum, palladium, or rhodium. These precious metals are the actual catalysts. The housing of the catalytic converter is made from heat-resistant, high-grade steel. Between the ceramic monolith and the housing is a pliable mat made from a mineral material. This protects the ceramic from impacts and vibrations. The catalytic converter reduces the levels of the following pollutants in the exhaust gas: carbon monoxide, hydrocarbon residues, and nitrogen oxides. Click on a nitrogen oxide molecule and follow the reactions. At the catalytic layer on the ceramic monolith, the nitrogen oxides lose their oxygen atoms and are converted into nitrogen. As the nitrogen releases oxygen, this process is called reduction. We say, therefore, that the nitrogen oxides are reduced to nitrogen. Now click on the carbon monoxide molecule. The carbon monoxide combines with a free oxygen atom. It oxidizes to form carbon dioxide. When a substance takes on additional oxygen atoms, this is referred to as oxidation. Have a look at oxidation and reduction again. So what happens to the hydrocarbon residues? Click on the hydrocarbon molecule. The hydrocarbons are oxidized to form carbon dioxide and water vapor. Because of these three simultaneous chemical processes, the catalytic converter is also known as the three-way catalytic converter. For all three of these processes to proceed correctly in the catalytic converter, the exhaust gas composition needs to be as uniform as possible. Therefore, the engine control unit monitors the exhaust gas composition by means of oxygen sensors and controls the mixture formation accordingly to ensure lambda equals 1. If this weren't to happen, one pollutant group or other would be left over, depending on the mixture. If the mixture were lean, nitrogen oxides would remain, and if the mixture were rich, carbon monoxide and hydrocarbon residues would be left over. The air-fuel mixture delivered to the engine doesn't always correspond 100% to the stoichiometric ratio of lambda equals 1. Therefore, the engine control unit measures the residual oxygen content in the exhaust gas using an oxygen sensor and regulates the mixture accordingly. If the residual oxygen content is too high, the mixture is made richer. If the residual oxygen content is too low, the mixture is made leaner. As the mixture is being corrected all the time, The oxygen sensor signal, which responds to the residual oxygen content in the exhaust gas, is continually oscillating between rich and lean within the so-called lambda window. Now draw the curve of the oxygen sensor signal into the diagram by alternately making the mixture lean and rich. Use the buttons to do this. The two-step oxygen sensor, known also as the voltage jump sensor, is used on petrol engines, utilizing lambda equals 1 closed-loop mixture control. It extends partly into the exhaust pipe and registers the residual oxygen content in the exhaust gas. The sensor consists of a ceramic body impermeable to gas and open to the fresh air side, as well as an inside and outer electrode. These electrodes enable the sensor to respond to the different oxygen concentrations in the exhaust gas and the outside air. Since the oxygen concentration in the outside air is considerably higher than that in the exhaust gas when the engine is running, an electrical voltage is generated between the two electrodes. From this voltage value, the engine control unit is able, in turn, to calculate the residual oxygen content in the exhaust gas. The integrated sensor heater quickly brings the sensor to the required operating temperature after the engine has been started. In addition, the heater enables the oxygen sensor to be placed a greater distance from the engine, which improves the service life of the sensor. The oxygen sensor upstream of the catalytic converter is used for lambda control. The signal from the oxygen sensor, located downstream of the catalytic converter, is used to check the efficiency of the catalytic converter. When the catalytic converter is operating, the voltage signal from the oxygen sensor downstream of the catalytic converter fluctuates considerably less than the signal from the sensor upstream of the catalytic converter. Because of the different tasks that they do, the two sensors are also known as the control sensor. This is the sensor upstream of the catalytic converter, and the monitor sensor. This is the sensor downstream of the catalytic converter. Now compare the signal of a simple voltage jump oxygen sensor with that from a broadband oxygen sensor. To do this, click on the two diagrams. The two-step lambda oxygen sensor indicates whether there is a lack of oxygen in the exhaust gas when the mixture is rich, or whether there is an excess of oxygen when the mixture is lean. However, the engine control unit can only evaluate the sensor signal in a very narrow range around lambda equals 1. As soon as the range around lambda equals 1 is left, the signal only changes very slightly, with the result that it's no longer possible to determine lambda. This is why the simple voltage jump sensor is only used on petrol engines with lambda equals 1 closed-loop mixture control. The simple voltage jump sensor is not suitable for use in engines which are also operated in the lean control range. In these engines, a broadband oxygen sensor is used as the control sensor upstream of the catalytic converter. The broadband oxygen sensor sends a signal which varies continually over a very wide lambda range.